In this lecture, we will continue to work with sequential circuits, and we'll discuss how we can implement finite state machines by describing them with VHDL. We will see how we can describe both Mealy machines and Moore machines. A finite state machine is a machine that can be in exactly one out of a finite number of states. To define a finite state machine, we need three things: a list of all possible states of the machine, a list that describes how and when we should change state, and also we need to specify the initial state of the machine. This is often visualized in a state diagram. So here we have all the states enclosed in the circles. We have the arrows that shows the transition, and we also have one arrow that shows the initial state of the machine after a reset. When we implement a finite state machine by using digital circuits, we can divide our circuit into three parts. We have a combinational circuit that generates the outputs from the machine. We have one combinational circuit that generates the next state. And we have some memory that stores the current state of the machine. When describing a finite state machine in VHDL, a good and common style to use is to divide the description into two parts. So one part is the combinational part, that is the output logic and the logic for generating the next state. The other part is the memory of the finite state machine. So what we can do in VHDL is that we define one process for the combinational part and one process for the memory part. By partitioning the system like this, it will become easier for us to debug the description. Also, by using processes, we are allowed to use if statements and also case statements. And this will give us a nice way on how to describe the transition between states and also the output in different states. When you designed finite state machines by using pen and paper, you might remember that before you could get the logic functions for the next states, you needed to code your states by using some coding scheme. When you describe a finite state machine in VHDL, you typically don't apply any coding scheme. Instead, you let the synthesis tool do this for you. So what we can do in VHDL is that we can declare a new data type that is suitable for describing our finite state machine. The declaration of the new data type is done in the architecture part of our module before the keyword begin. Here is the syntax that we use to declare a new data type. First we use the keyword type, then we give a name for our new data type. Here we have named it state. Then come the keyword is, and then we list all the possible values for this new data type. So here we have input three labels: start, pause, stop. Later on we can create a signal of this new data type, and this signal can now only take on the value that we have specified for this data type. The actual coding scheme that will be used for our data type is decided by the synthesis tool, and the coding applied could then also be optimized by the tool to reduce, for example, power or increase the speed of the circuit by using some heuristics. We will now go through the complete description of a finite state machine. So the machine that we will describe has two states, state 1 and state 2. It has one input, in1, and one output, O1. The state machine also has two other inputs, the reset and the clock. So we start with describing the entity of our finite state machine. So RST is the input reset signal, CLK is the input clock signal, then we have the input in1 and the output O1. Then we create a new data type named state. So this one can take on two values, state 1 and state 2. We will then use this new data type to declare two signals, the current state and the next state. So the signal named next_state is connected to the output of the combinational circuit that generates the next state. And the signal named current_state is a wire with memory. So this is the output from the memory that keeps the state of our machine. Then we describe the combinational part of our finite state machine. That is, the part that should generate the output of the finite state machine and also the logic that should generate the next state for our machine. So we can describe this part by using a process. So the process should be activated when either the input change or when the current state change. So we list these two in the sensitivity list of our process. Then we give a default value for the signal next underscore state. So if nothing else is given in this process, the next state should be the current state. So this describes the looping transition that we have above each of the two states. Then we declare a case statement by using the keyword state. And then depending on the signal current underscore state, we will decide on some specific cases. So when current state is equal to state 1, the output O1 will become 0. And if the input in 1 is equal to 1, then the next state is state 2. When we are in state 2, the output O1 should be 1, and if the input in 1 is equal to 0, then the next state should be state 1. So note here that in this process we generate values for the output O1 and the signal next underscore state. Then we will describe the memory part of our finite state machine. So this we can also do with a process. So this process should be activated whenever the reset signal changes or when the clock changes. So here we have decided on an asynchronous reset. So first we check if the signal RST is equal to 1. If that is true, we will set the current state to state number 1. Else we will check if it is a rising edge of our clock signal CLK, and then we will update the current state with the value of the next state. A common beginner mistake when describing finite state machines is that the designer forget to always assign value to the output of the combinational part of the finite state machine. So this is almost the same combinational process as we saw earlier, but here we have skipped the default value after the keyword begin. So the problem here is that we don't always assign the signal next underscore state a value. For example, if we are in state 1 and in 1 is equal to 0, the signal next underscore state will not be given a value. And when we run this through the synthesis tool, the tool will detect this and it will think that we will like to have some memory on this signal. This means that we will get a latch on the next state signal. This is not what we want. And the tricky part is that when you run a simulation, it might seem like the circuit performs as intended, but when you later on download the configuration to an FPGA, you get a really strange behavior where the circuit sometimes behaves as intended, but other times it doesn't. So typically you will also get a warning, so keep an eye out for this. And my tip to you is that always set default values for the next state signal and also for the output of your finite state machine in the combinational part of your circuit description. The finite state machine that we described in the previous example was a Moore machine. We can also describe a Mealy machine in VHDL. So the difference between a Moore and a Mealy machine is how the output are generated. In a Moore machine, the output only depends on the current state, whereas in the Mealy machine, the output not only depends on the current state, but also on the current input. So if we will get a Moore or a Mealy machine depends on how we describe the generation of the output signal. So as we saw in the previous example, we had a Moore machine, and here the output only depends which state we are in. So if we are in state 1, the output O1 is equal to 0, and when we are in state 2, the output O1 is equal to 1. If we were to implement this as a Mealy machine instead, we could do like this. So when we are in state 1, we assign the output a 0, but if the input in 1 is equal to a 1, the output will also be a 1. And when we are in state 2, the default value for the output is that O1 is equal to O1, but if the input in 1 is equal to 0, the output will also be 0. So here the output depends on the input